quando a gente vem da zona urbana para cá, a gente não acha que o mundo dele seja pequeno, mas que a gente pode ampliar esse mundo dele através da tecnologia. Então não justifica um aluno no 6º, no 7º ano, já praticamente para o ensino médio, tendo que pegar o que tem e o que não tem para ir para Campo Maior, para poder ir para uma lan house, tendo que ir para debaixo de uma árvore. Isso não justifica.
O Brasil ainda tem muita gente desconectada, tem aí para mais de 100 milhões de pessoas que ainda não têm acesso à internet e que estão em áreas remotas. O Loon vai ser muito útil trazendo as antenas voadoras que enxergam as áreas de cima e não tem toda a dificuldade de atravessar florestas ou atravessar montanhas.
Preciso incluir meus alunos nessa era digital, porque só assim eles vão crescer quanto estudante, quanto pessoa e poder trazer o crescimento para a própria comunidade dele.
Agora que eu não vou embora mesmo daqui da Água Fria.
Welcome, everyone. My name is Pavni Divanji. I'm a VP of Engineering here at Google. And it is an incredible honor for me to be introducing this Women Techmakers panel. Women Techmakers, as you probably know, was formed by Natalie here and Megan Smith, who used to be one of our VPs of X, who's now CTO of US, to inspire, to connect, and to celebrate all the developers, women designers, women entrepreneurs, all women in tech. And we've done a lot of events to really shine the spotlight on some incredible women. The last one I had the honor of attending was at the International Women's Day this year. And I was blown away. We had 10,000 women participate, and it was a truly global event. We had 128 places where we hosted these events across 50 countries. So we have a huge amount of momentum. And it makes me incredibly proud when I see the number of women at I/O. I think we have grown it 4 times in the span of 3 years. So it is truly a huge achievement. And last year, we were at I/O. I was right here on stage introducing a robotics panel, which was also equally popular and well attended. And this year, we have even a more fun topic for you. We have today our Loon team, which is one of our ambitious moonshot projects at Google. And the question they're attempting to answer is, could we get everyone connected on the net, across the globe, no exceptions, no matter how remote you are? So with that, please join me. I wanted to introduce 2 of the extraordinary women of Loon. One is Sam, who's our aerospace engineer and is working on the simulation of balloons, and Wanda, who's a senior software engineer, and who is the mastermind behind the infrastructure of Loon's mission control system. So please join me in welcoming them on stage. Thank you.
Thank you, Pavni. So yeah, we're here from Project Loon. I'm Sam.
I'm Wanda. Hi.
And we wanted to tell you a little bit more today about how we engineer for the Stratosphere. This is the older deck of our slides. Sorry, 1 second. This is the old deck.
Sorry for the interruption.
Yeah. So you guys enjoying I/O so far? you. Good. See if we can.
Just try, drive it. Oh,
Yeah.
just keep going. Just keep going.
Do you want us? I'd rather use the right deck, but anyway. Okay. I don't know what version this is.
We can just go, yeah.
All right.
Go.
Okay. All right, so who here has ever had bad reception? Good. So imagine never having reception at all, or having to climb a tree like that boy in the video in order to be able to get reception. This is the type of problem that we're trying to solve at Project Loon. We're trying to bring internet access to everyone in the world. The video that you just saw was from a demo that we did in Brazil last year in Agua Fria. And there were these 2 schools in the Amazon. These kids had never seen the internet before. And for 2 weeks, our team went down there. We flew a few balloons over that area. And these kids were able to connect to the internet for the first time. We actually did an interactive geography lesson in their class. They were learning about Portugal, and they were able to pull up some maps from Wikipedia and some other resources online to supplement their lecture. And it was really amazing just seeing their reaction to be able to see what the internet could really provide for them. And so that's part of why we do what we do. On this map here, you can see that these are the areas of the world that currently have internet access, where internet access is prevalent. But most of the world is still in the dark. 2 out of every 3 people in the world don't have access, especially people living in rural and remote areas. So this is a problem that we want to solve at Project Loon. And access is really important because access can provide so many things at your fingertips, like the world's information at your fingertips. All of the resources like health information, educational opportunities, tools for small businesses, just things that you need to be able to provide for you and for your family. And so the biggest problem with bringing internet access to rural and remote areas is that the current infrastructure, such as cellular towers, are really just not cost effective in some of these areas, or just impossible to install. Like being able to reach islands and mountains and areas that are very remote is very difficult to do with just current ground infrastructure. And a lot of these areas, the current solutions involve using satellites, which are very expensive. And most of the people living in these areas are just not able to afford the connection options that are there now. So at Project Loon, we decided to try this radical new approach, which is to be able to fly balloons that can float in the stratosphere over some of these areas and beam internet down to the ground, providing internet connection at a fraction of the cost of current infrastructure. So how does Loon work? The idea behind Loon is that these balloons will float over rural and remote areas. And as they pass over these areas, users will be able to connect directly from their LTE handsets. So no special antennas or anything is needed. You just need your phone, and you'll be able to hook up to Loon internet. And as each balloon flies over, the balloons actually move with the winds. They're constantly in motion. And so the balloons will be floating over these areas. But as one balloon leaves, we have to have another one come and take its place, which means that we need to adjust this entire fleet of balloons as a network. And in the stratosphere, we actually have winds going in different directions. So depending on what altitude we're flying, we're able to catch different currents of wind to be able to navigate these balloons to areas that we need to go. So all of this takes a lot of effort and computational challenges. And we've built a mission control infrastructure that allows us to do planning and simulation and control of these balloons. So that's the team that Wanda and I work on. And we're going to tell you a little bit more about that today. So Wanda, she's one of the senior software engineers on our project. And she's really awesome. And she's going to tell you a little bit about mission control.
Thank you, Sam. So in my opinion, the coolest thing about our project is that we name our balloons after birds. Here is Ibis, the bird, and here's our balloon that we built. It's also named Ibis, and we built it and launched it into the stratosphere. It can go as high as 25 kilometers up in the sky. It's about 3 times the height of Mount Everest. It gets pretty cold up there. It can get below 80 degrees Celsius, so we want to make sure that our balloons can stay healthy. We have also observed the balloons going as fast as 324 kilometers per hour. It's about the same speed as the fastest animal on the planet. Does anybody have a guess what that is? Peregrine falcon can dive down. It's also another bird, in case you don't know. It dives to catch its prey over 320 kilometers per hour. So because it goes so fast and it gets, the weather condition is so cold up there, we want to make sure that our balloons can be tracked and also stays healthy. So our team built a mission control system to monitor its every move. So when I mention mission control, this is probably the view that you have in mind, right? Like maybe with some cheering in the background. Hey, we launched the balloons. But what we actually built is a mission control system that can run on workstations, handheld devices, and cell phones so that we can track Ibis anywhere we go at any time. So it sounds simple enough, but our mission control system is actually quite complicated. This is a flow chart of only the high components of our system. It can do communications with the balloons, processing telemetry, and it can also monitor the health of the balloon, the simulation, navigation, controlling the balloon, and a simple UI that will be able to help us to be able to read it more carefully. So here is a glimpse of our mission control system. As you can see, Ibis is traveling across the Atlantic Ocean, heading towards South America. And the red line shows the historical path that it has traveled in the last 24 hours. And the pink line is the predicted trajectory of this balloon in the next several days. So we actually make predictions, which I'm going to talk about later on in this talk. So our primary customer for the mission control system is our flight engineers, who work 24/7 to monitor our fleet of balloons in the air. So we want to make sure they're happy, and we also want to make their lives a little easier, so they're not staying up all night monitoring our balloons. So we built several features to kind of enhance this. So in this picture, in this screenshot, basically the lines here represent the air traffic control center boundary. So they can monitor and make sure that our balloon, Ibis, is not entering another airspace anytime soon. And when our mission control system detects that the balloon is about to enter another airspace, it will automatically generate a flight control plan and email it to the next air traffic control center. And our flight engineer on call will be able to get an automatic alert so they can start calling the local authority and start doing the coordination to make sure that they're aware of our balloon entering their space. So now that you have seen how we track our balloons and monitor them, we do have some stuff that we cannot easily monitor directly. So Sam is going to tell you a little bit about how we diagnose these kind of cases. Go ahead.
Yeah, so as Wanda mentioned, our balloons are 20 kilometers up in the stratosphere. The environment there is very cold and harsh, and we only really get very limited information from our sensors. So we fly different sensors like GPS and pressure sensors, but there's a whole lot of other stuff that we want to be able to estimate about our balloon state. So I've been working on different estimation algorithms that we can use to try to figure out things like temperature and how much gas we have left in the balloon. And I'm going to go over a couple of these examples, the more interesting ones, I think, next. So one of the most important things that we need to figure out is how long our balloons are going to be able to last up there. What is our balloon lifetime? And since we want our balloons to be able to last up there for hundreds of days, we've designed superpressure balloons. So this means that the gas inside the balloon is at a higher pressure than the ambient, and the gas particles are pushing against the walls of the balloon, giving it its shape. Now, the pressure inside the balloon depends on both temperature and the amount of gas in the balloon. When it's really hot or when there's too much gas, the balloon could potentially burst. So it's really important to know what temperatures we're going to expect to see during the course of our flight in order to decide how much lift gas to fill the balloon with. Conversely, when it gets too cold, or if we've lost too much gas, the balloon could actually lose pressure, especially at nighttime when it gets cold, and it could essentially not provide buoyancy anymore by not having its fully inflated volume. So this is also undesirable. So we need to be able to monitor these two quantities very carefully, but they're very difficult to estimate up in the stratosphere. So traditional methods of measuring temperature, like putting a thermostat on your wall in your house, don't really work in the stratosphere. we're above 95% of the atmosphere, so the air is really, really thin up there. So the thermostat on your wall works mainly through convection. Air rushing past the sensor, you'll be able to read the ambient temperature of the air. But for us, we're measuring mostly radiation. And so as the sun comes up and shines directly onto the sensor, you're actually reading more of like the radiation of the sun than you are the lift gas temperature inside the balloon. So the red line over here shows you the readings from our sensor, and the blue line is actually closer to what our balloon temperature is. So the sensor is kind of useless during the day, which is a problem. So in order to fix this, I built this thermal model that essentially takes in all of the sources of heat that affect our balloon. So things like the radiation from the sun, the earth, which is like a giant space heater heating us up, and then also interactions of the balloon skin with the film. So the way our balloon temperature works, it's similar to a car in a parking lot on a hot day. Like when you go to open the door of your car, it's really, really hot inside your car compared to the outside air. So our balloons similarly take in a lot of the radiation of the sun during the day and get really hot. And then at night, especially when we're flying over clouds, which block the radiation from the Earth, we can get really, really cold. So fusing all these inputs together, we can actually model very well what the temperature of the balloon is. And once we know temperature, we can actually infer how much gas we have left. And by tracking this day after day, we can see what leak rates we have and project forward to see how long our balloons are going to last. So here's a few examples of the graph that, of the different graphs that come out of our estimation algorithms. So you can see temperature on the top, and then pressure as it decreases over the balloon lifetime, and gas level, and finally the estimate of how much lifetime we have left. Another really important quantity that we would like to know is the state of our batteries. Our balloons are 20 kilometers up in the air. You can't really plug them into a wall and charge them overnight. And so we actually need to be able to provide all of our own power. So we fly solar panels that can capture energy of the sun during the day and store it in our batteries to be able to operate all of our systems at night and also do different maneuvers. And monitoring our power is actually really complicated. Our systems are very complex. We have several different boards, lots of different sensors. We have batteries, we have solar. And we also have heaters on board that turn on when it's cold. And so predicting how much all of these components are going to consume is quite difficult. And then batteries are actually very, very difficult to model as well. This curve on the top here shows you all of the different discharge curves for the exact same battery, but just under different temperature and load conditions. And there's about a 35% difference depending on whether the battery is cold or hot. So batteries do not like the cold and actually perform quite poorly in the cold. And we need to be able to estimate our temperature for our battery as well as how much state of charge we have left under all of these different varying conditions. So my team and I built a state of charge estimator that actually works a lot better than our old system. Before, we used to use a chip that was designed mainly for cell phones. So it's very similar to like the chip that your cell phone would use to tell you how much battery you have left. And yeah, it's the operating conditions of our balloon involve really, really extreme temperatures. So the chip was really not performing very well. So we had to build our own in-house state of charge estimator that performs a lot better than the system that we were using before. And then the second piece of this is modeling how much solar power we're going to get from our panels. This is actually fairly complicated because it involves trying to figure out what the solar elevation will be for different latitudes and longitudes, how much the atmosphere is going to affect the solar radiation and how much attenuation we're going to get from that, what our balloon shadow is going to look like. So actually, when you put it all together, you end up with this Batman-looking curve where as the sun comes up, you get more and more radiation and less attenuation from the atmosphere, which causes the initial rise. And then after a certain level of elevation, the balloon will actually kind of come in the way and cast a shadow on the panels. So that causes the drop, the ear of Batman in the curve there that you see. And so putting it all together, we actually have a fairly decent idea of how much power we're going to be generating and consuming, and we can use this in our simulations to predict our power budget and how much we have available for maneuvers. So once we know what the health and the status of the system, we also need to be able to predict where Ibis is going to go and how we're going to navigate to different areas to be able to provide continuous coverage. So Wanda's going to tell you a bit about our simulations.
So in order to navigate Ibis to a desired location to provide continuous coverage, we have to first be able to predict where it's going to go in the future. So by doing that, our balloons actually fly with the wind. So to do that, we actually try to get information like the wind data from NOAA, which stands for the National Oceanic and Atmospheric Administration. The data that we get from NOAA is public information, and it is available to pilots. It tells us about the speed and the direction of the wind in the air at different levels of the stratosphere, actually. So here's actually a visualization of a wind map that we built for a small cubic area in the sky that basically tells us where the wind is actually going. So we fetch the forecast wind from NOAA every 6 hours, and the data that we get contains 16 days of data in the future. So basically, we have to build lots and lots of these maps that cover the entire surface of the Earth for the next 16 days every 6 hours. That's a lot of data and a lot of processing, but the good thing is that we work for Google, so we have a lot of compute resources that we can utilize here. So here is a simulation trajectory of Ibis. The black arrows basically is the wind direction and the speed at that position. And as you can see, the red arrow is the movement of Ibis as it flies with the wind. So besides the position, the altitude information, and the wind data, we also consider things like the battery power, the health condition of the balloon to determine the balloon duration while we're making this type of prediction. With the knowledge of the wind patterns and ability to navigate the balloons to get to a desired location to provide coverage, we can basically move the balloon up and down, in this case, to do navigation. So in this picture, we have a reachability map that we built for Ibis at different levels of the stratosphere. So each one of these trajectory basically represents the Ibis's path at that altitude level. And so basically at each point of the computation, we can decide which level of altitude we want to move Ibis to get to a desired location. So my team have actually built lots and lots of these algorithms to try to navigate the balloons optimally. So this one algorithm that we use in this example is called the Crazy Simple Planner. And what it does is simply uses a form of heuristic spanning tree search algorithm to try to find the most optimal path from one location to another. So in this case, we're trying to find the cheapest cost trajectory, and it's defined by the user. The cost can be defined as either the destination that you want to get to, or the altitude band that you want to keep the balloons at, or it can also be the power consumption to get to a location. In this particular example, we want to try to find the shortest path from Australia to Christchurch in New Zealand. So the white lines here indicates all the possible trajectories, and the red lines is the one that our algorithm, our Crazy Simple Planner, has selected to be the most optimal path. So everything looks great, right? Like we want to direct the balloons to New Zealand, it's doing that. But life is not that simple, right? Because the wind is forecast, it's never totally accurate. So we want to plan for the uncertainty. One of my colleagues actually built a wind noise model that will be able to kind of throw us off a little bit when we're doing the simulations and prediction. So the red lines here represent all the possible trajectories at that altitude level if we are trying to simulate balloons at that level. And the blue line is for a completely different altitude. So for our stochastic planning algorithm, we try to find the best fit for that altitude by throwing in some wind noise. So now that we can navigate Ibis to Christchurch, what happens if it leaves? Are we going to get interrupted internet coverage? We want to make sure that when a balloon leaves, another balloon, that's a Merlin, is going to come in and provide coverage for the people below. So we have to provide another mechanism to flock the entire fleet of balloons from place to place in order to provide continuous coverage. So in order to validate our fleet planning algorithm, I built a analysis planning framework that will be able to, run a sizable fleet and simulate it and be able to do some analysis over our algorithms to make sure that it's doing what we are thinking it's doing, under a reasonable amount of time, because it's easier to do simulations, but it's not easy to actually run thousands and thousands of these balloons under a certain amount of time. So in this example, this is generated by my planning framework. We're trying to launch Australia. We're trying to launch out of Australia and to cover the coverage in Chile. And in this picture, you can see like this small, like a couple dozen balloons is coming out of Australia, heading over to Chile at different directions because the wind is actually going different directions. So this tool helps us to be able to predict the wind patterns at different times of the year. And we can also try to do this in various different ways so that we can launch balloons out of different cities and be able to evaluate the different launch sites for our experiments. In this example, we're flocking the entire fleet of balloons and trying to keep them around the equator. And Ibis is going out of course a little bit, so our planning algorithm actually tries to redirect it back on course. So in our most recent long-distance LTE test, we were able to launch one balloon out of New Zealand, and it went around the world over 20,000 kilometers, and be able to come in within 500 meters of ground distance and provide over 2 hours of internet connection. It was a huge success for our team. So in the future, we're hoping to fly like thousands of these balloons and be able to have this kind of success. But that also means we have to hire more flight engineers. So to make them happy, we want to make sure that we can actually automate the process of navigating our balloons. So my colleagues and I built a flight automation system that will be able to automatically control the balloons to go up and down in order to reach its perspective goals. So with the system that we built, we're hoping that it's a small step toward providing continuous coverage for remote areas like Aquafria that you saw earlier in the video. We want to bring internet to everyone, everywhere, like for those kids that you saw. We want them to learn not just as students, but also as human beings in this world, like all of us here. Thank you very much.
Thank you.
So now we're going to welcome our moderator, Natalie, and a few other ladies from Project Loon to answer a short Q&A.
Thanks. Good job, really good job. All right, so thank you. So you want us guys right over here.
Okay, go ahead.
We'll do a little dance.
Thank you, guys.
Hey everyone, I'm Natalie. Can we have another round of applause for unexpected slides popping in? I think you navigated that just as well as you do the balloons. Very, very nicely done. So my name is Natalie Villalobos. I run the Women Techmakers program at Google, as Pavni mentioned. And the whole purpose of Women Techmakers is to increase the visibility, community, and resources for women in technology. And so I have the pleasure of sitting down with some of the world's innovators and sharing their knowledge with you. So we've collected some questions from friends out at I/O and on the web, and I want to get started with a couple good ones. So we've heard some of the computational challenges that you went over in the talk. Can you tell me a bit about the operational challenges? And I'm going to scoot back. Who are you? Let's start from the end.
Hi, everyone. My name is Maria. I've been at Google for almost 4 years, and I joined Project Loon last July as a technical program manager working on the avionics team.
Hi, I'm Tamron Stuber. I'm a program manager focused on manufacturing operations of Loon. I've been on the project for about 3 years.
And I'm Olivia. I work on scaling operations, mainly at the intersection between hardware and operations.
Now we can get started. Okay. So, computational challenges, but can you tell me some of the operational challenges? Because this isn't just a two-woman show. I mean, Loon is a huge team, but specifically, some of you focus on the operational side. So can you speak to that?
Sure. Like I mentioned, I work on scaling operations. So one of the bigger challenges is how do we actually launch at scale Not only do we need to figure out where in the world we launch these from by studying ground weather patterns where wind speeds are lowest so that our balloons don't turn into giant spinnakers when we launch them, where it doesn't rain so our electronics don't freeze, where there isn't a lot of cloud cover. So that's one big thing. And then we also just engineered something called the birdhouse, which is a 50-foot tall mobile boat hoist that we engineered to actually automatically launch our balloons. So taking our 45-minute, 15-person operations crew down to 4 people monitoring our launching, which is pretty incredible.
Yeah, it's like a great sign of optimization. So what are the challenges involved in building the balloons, actually constructing them, the components that have to keep them in the air for the next 100 days?
So there's actually a lot of challenges with manufacturing the balloons. There's a very small industry of balloon makers. There's only a handful of companies that are scattered across the world. And the traditional process for balloon making is quite manual and artisan. And nobody's ever really had to build at the scale that our project's demanding. So like we're quite literally pushing the envelope of current industry standards. So once we kind of graduated out of being just this harmless science experiment, as we used to call ourselves, you know, we really started looking at like how we can really scale the manufacturing process. So we really started looking at every industry for inspiration of how to automate, how to scale, how to improve quality, because these balloons are massive. They're about 45,000 cubic feet, and they're made up of 1.5 mil polyethylene. So they're actually pretty fragile, and they can be brought down by just a small pinhole. So a good comparison that we like to make of, you know, how we manufacture this is how you would manufacture a parachute. You can't really test it right before you use it. So you have to instill a lot of quality processes, you know, all these controlled checks during the manufacturing process to guarantee that it will work. So there's a lot of challenges, and there's not really this like clear path laid out for us, but honestly, that's what makes it fun.
So, and these are open for anyone on the panel. So how do you get them to last for so long? 100 days is a pretty long time, and Mother Nature is obviously also an obstacle. So longevity, how do we make it happen?
So kind of what I just spoke about, honestly, it's really having this strong eye of detail. You know, we've pulled from a lot of just even paying attention to, so these were pretty manual for the first year, and we actually had a team of people that were building these balloons and actually having to crawl on top of them. So we realized that like we're getting these little pricks, and they were kind of in the shape of toenails. So we actually had them wear these little like fluffy fleece socks. So it's like that little eye of detail of like looking at everything to get them to stay up.
And so kind of arising from the operational creation side, can you tell me what's your favorite story about your time being on Project Loon? It's like nervous laughter.
I think you have one. I think Sam has one.
I mean,
There's so many good ones.
so there's a lot that we can't share. But one that I can share that was pretty hilarious was actually, so we actually started building these balloons in-house by a team of like scrappy engineers and different backgrounds. And so we were building the prototypes in-house, and we'd get them off the ground, they wouldn't make it too far. But as they started kind of scouring the distance of the United States, we were tracking one that had kind of reached its farthest. It was actually over Kentucky. We started getting these like YouTube alerts of UFO sightings. And actually in their local news, they actually were having a UFO sighting, and it had this image of our balloon. So that was one of my fonder moments.
There's actually a whole website, I think, dedicated to Loon.
You guys should look at it.
Loon UFO
Pretty hilarious.
So I was also told about Batman symbols.
Yeah.
So you already referenced Batman in your slides, but I think that there's some other story about Batman.
Well, so internally we call Sergey Batman just because he's kind of cool and awesome.
Sergey Brin.
Sergey Brin, the Google founder, who he's in charge of X. And so I'm not even sure he's aware of the nickname. But anyway, for April Fool's Day, one of our UI engineers changed all of the symbols of our balloons into Batman symbols. So on our live mission control map, you could just see a lot of Batman symbols instead of balloons.
Nice, and cool, no, I really like that. So kind of flipping back, what do you characterize as your team's biggest challenge? So clearly, like, you're testing, you're iterating, and you're having fun along the way. But what are some of the challenges that you faced, and what was the success that eventually overcame that challenge?
Yeah, I can take that one and speak a little more on the engineering side. So kind of the diversity of work, as we have heard from this panel, that's required to make Project Loon a success is really enormous. Sundar touched on this yesterday in his keynote. You know, some of the biggest challenges is the balloon duration, kind of the range and the bandwidth of the signal that we're trying to provide, as well as balloon-to-balloon communication. So the last one is particularly important because in order to meet our really ambitious goals of providing internet for all, we need to essentially create a network of balloons in the sky, just like there is currently a network on the ground. The technical challenges to be able to send and receive signals between balloons is one certain challenge, but to be able to launch the hardware, make it operational, and provide the high quality and high accuracy signal, you know, 60,000 feet in the air in environmental conditions that are essentially alien for us, that's a really different ball game, essentially. But we're making it happen. We proved that it works, and as some would put it, it's freaking awesome. Pretty good.
So when I was talking to Pavni earlier, and she focuses on our Google for Kids effort. And we're doing a lot this year. We did last year. We had an IO Youth, where we engage young minds into what we're all developing, because they're going to grow up and they're going to inherit this world from us. So, to those young people that might ask this question, you know, did you always want to be an aerospace engineer? Like, what did you want to be when you were younger? What did you think you would grow up to be?
Well, I never really wanted to grow up. And fortunately, as a Google engineer, I haven't had to. But yeah, no, I always really liked math and science, and I didn't really know what engineering was when I was in school. I figured I wanted to be a physicist or a scientist. And yeah, after going to college and just kind of checking out some of the engineering classes, I found it a lot more appealing to have science as applied to making something and something tangible, where it really feels like you're playing with toys. You're like building and creating something new. And so yeah, I fell in love with engineering right there.
So for me, I was actually pre-med all through half of my college years. And then I took computer science classes as an elective, and I loved it. So it was really interesting, and I just continued down that path.
Cool. Olivia?
So I wanted to be a professional horseback rider when I was a kid, which makes sense why I'm at Google now. But I didn't want to specialize in anything, and being on a team that's doing something that's never been done before makes me come to work and get challenged every day and learn something new, and I get to try everything, and that's really satisfying. So I haven't had to grow up either.
So I actually wanted to be a fashion designer since I was 8, and that's actually what I went to school for and worked in the fashion industry for the first couple years. But it just wasn't quite right and wasn't quite feeding me in the way that I wanted it to feed me. So I stayed really open and was just like trusting and hoping like the right thing would come forward. And actually my apparel construction skills were what led me to get recruited onto this project. So I thought it was a good lesson of like following your passions but staying open and not always having to have it figured out. But yeah, so it's been great.
Yeah, I didn't know what I wanted to be either when I was in school. I was just one of those people that try to do my best and just work extremely hard. But one of the qualities, I guess, that I've had and I have kept is just really being open to different opportunities, different experiences, trying to be flexible in that way. So I remember kind of a turning point for me was back in high school, after my junior year, that summer there was a program that was sponsored by the New Jersey government and Rutgers University called the Governor's School of Engineering and Technology. So being part of that 1-month-long program was kind of the first time that I got exposed to engineering principles. I was taught how to, the concepts of abstraction and logical thinking that comes with programming, and also how to build something physical. We were using Lego Mindstorms. That really attracted me to this sort of field. also doing that together in a team, and I was kind of hooked on tech since then.
Wonderful. So I know I speak on behalf of Pavni and thank everyone in this room. Thank you so much for leading this new field of innovation, and we look forward to seeing more of what you create in the years to come. Thank you.
Thank you.